Hello everyone, welcome to Rooted in Purpose. In this video, we'll be learning how to find the length of any curve. So firstly, we'll be learning the concept behind it and then we'll apply it into several problems. So let's get started. Okay, so let us learn the concept now. Suppose I have a curve. So this is my curve. If I take a really small element, infinitely small element from this, so this is my infinitely small element, and if you zoom it, so let us zoom it now. So zooming it will give you like this. If I zoom it, I will get a like this one is the smaller element, this is a curve. This is my curve y equal to fx. This one, if I do like this, I'll get a triangle, right angle triangle to be specific. This one can be considered as dx and this one is dy. So if I want to find the length of the curve, say dt, I will integrate dt and I will get the length of the curve. What is dt? So dt, according to Pythagoras theorem, dt square is equal to dx squared plus dy squared. So dt is the under root of dx square plus dy square. So this is how we'll be finding it. Now let us apply this in the problem here. We have a straight line. Straight line is y equal to x plus 1. This point is 0, 1 and this one is 2, 3. So whenever we will try to solve certain problems, we'll be using parametric form. So according to parametric form, if I suppose x to be a, if I suppose x to be a, I will get y is a plus 1, right? Now I will differentiate both sides. So what I will get? Dx is dA and dy is again dA. So simply integrating it will give us what? So just to apply it here, our length of this thing from this curve is integration of dt, which is nothing but integration of dx square plus dy square, which will give us under root dA square plus dA square, which is nothing but root 2 times of dA, and will integrate it. Now suppose I want to find the length of this curve from this point to this point. So in this, what is dA? So what is a changing from? A is nothing but it is x, right? And x is 0 to 2. So I will integrate from 0 to 2. So what it will give us? It will give us root 2 times of a, and here we'll put the limit from 0 to 2. So we'll get 2 root 2. Now let us verify this through Pythagoras theorem. So when we go through Pythagoras theorem, this length is nothing but 2 and this length is 3 minus 1, which is again 2. So according to Pythagoras theorem as well, we'll get 4 plus 4 rooted, which is nothing but 2 root 2. Now let us apply this concept on other curves as well. So for the next example, I have taken a general circle with a radius a. So what are these points? This point here, it is 0, a. This point here, it is a, 0. So if I want to find the length of the whole circle, can I do like that? If I find the length of this one, in the first quadrant and then multiply it by 4, I will get the length of the whole circle. So we'll be doing that. We will find the length of the circle in the first quadrant and then multiply it by 4 and get the required one. So before going further, I want to tell you that finding the length of any curve is simple when you know the parametric form to use. In this one, the standard parametric form for a circle is x equal to a cos theta and y is equal to a sin theta, and I will use this one. How do I get that, right? So when you put this in this, you will get a square common. Inside is sin square theta plus cos square theta, and this value is 1, which becomes a squared, right? So this is correct. So whenever you apply parametric form inside an equation, you get this, and this is correct. So this one is the correct parametric form. So let us proceed further. We want to find dx and dy. What is dx? Dx is nothing but minus of a sin theta d theta, right? The differentiation of cos theta is minus sin theta, and dy is a cos theta d theta. Now I need to find the length of the curve, and we know that the length of the curve is under root of dx square plus dy square. So when I do this, I get a square sin square theta d theta square as well, a square sin square theta d theta squared plus a square cos square theta d theta squared. So this simply gives the integration of this, and yes, so next up we have integration of d theta comes out of the root, a comes out of the root, and inside the root we have root 2 a square d theta square common. Then we will have sin square theta plus cos square theta. So this is 1. Okay, so this is a times theta, and theta is, we know, from 0 to pi by 2. This is pi by 2 angle, right? So it's from 0 to pi by 2. It comes out to be a pi by 2, and when you multiply it by 4, you get the length of the circle. So multiply it by 4 will give us the length of the circle, which is equal to 2 pi a, and we know that length of the circle is 2 pi r, and we have confirmed this by integration. So if you know parametric form, if you know integration, if you know basic differentiation, you can find the length of any curve. So I think these examples are enough. Next I will tell you some of the parametric forms for different curves. Okay, so here are some standard parametric forms. The first one is ellipse, a general ellipse with a and b as coefficients, and we can put parametric form x equal to a cos theta, y equal to b sin theta. Here is a hyperbola, and we are putting x equal to a sec theta and y equal to b tan theta. What we are doing is, we are simply using trigonometric identities. So what are they? The first one is cos square theta plus sin square theta is 1. Second one is sec square theta minus tan square theta is 1. And there's one more identity, which is cosec square theta minus cot square theta is equal to 1. We haven't used this one here, but we have used this one and this one. So the first one is used here. The first one is used here as well in the circle parametric form. The second one is used here because we see a minus sign here, and by that we imagine that this identity can be used. And this one is a parabola, and we have put a t in both of them, which is a parameter. What is the main, what we want to do by this parametric form? we want to bring x and y into a common parameter so the integration can be done. If I have a line y equal to mx plus c, what I want to do is, suppose I have a x. If I tell that let x remain itself, and I have y in form of x, right? So what will be dy? Dy is nothing but it's m times of dx. And what is dx? Dx is dx as well, only dx. Now when I do under root of dx square plus dy square, I will get the integration in only one parameter, which is x. So that's what I want, and that's why I use the parametric form in every place to get a single parameter while integrating, so we can perform the integration. So that's it for the video. We'll be meeting in the next video. I hope you liked it. Thanks for watching.